This is going to be a video about resistors. So when we have current flowing through some kind of a circuit, if we've got just a wire, we are going to have a certain amount of current flowing through that. If we want less current to run through it, or if we want to actually use that current to do something, is the more likely option, then we are going to introduce resistors. So a resistor is something that resists. A resistor is something that resists the flow of current. And a resistor is a thing. It's a circuit element. The property of how good it is at doing this is called its resistance. This is kind of the effectiveness of a resistor. So, where the resistor is the thing, the resistance is the property. And resistance is measured in ohms, which get a capital omega. It sounds like a very unhelpful thing to have resistors in a circuit. I understand that the idea of why would I make a current just so that I can then decrease it? Why wouldn't I just use a smaller power source? Doesn't that seem like it would be the better option? I understand that that sounds like a good idea, a better idea. And, you know, there is the maybe just in case you have this battery and you can't get a smaller one. And so how do you make that current smaller? Well, I mean, I guess so, yeah. That's something you can do with it. But the bigger thing is pretty much anything that you put into a circuit, anything that's going to do anything, will have a resistance. If the thing has a resistance, then it'll act like a resistor. If I have a light bulb, and all I want to do is light it up, that light bulb needs current running through it, so we're going to get some amount of current running through it. And if we get enough current running through it, it lights up. Because it's, I don't want to say using because that makes it sound like there's less current coming out than there is going in. Because it's utilizing, that's fair, that current, it acts as a resistor. So we can say that this light bulb has a resistance of maybe 200 ohms, for example. And if we know the battery voltage, then we can figure some things out. There is an important point in here about current not being used up. So with a light bulb, this inner filament is connected this way and this way. Over here in between, you've got an insulator that doesn't allow current to flow. And then you've got a conductor and a conductor. So we have this light bulb set up, we have the inner wiring of the light bulb set up so that the current has to go all the way through it in order to get out the other side. Now I did say before that you can think of current as a chain of charged particles, each one taking the next location. What this resistor does, effectively, is make it more difficult for each of the charges within itself for each of those spots to be vacated. It kind of holds on to those a little bit tighter. But again, if those charges can't be vacated, if this one can't jump to the next spot, then all the way back down the line, this one can't jump to this spot, this one can't jump to this spot. Each one can only jump as fast as the slowest one, right? So a resistor doesn't do something to the current here without doing it everywhere, which means the current flowing into a resistor is the same as the current flowing out of the resistor. A resistor, we don't always use a light bulb. One thing we'll do, you'll find that a lot of circuit elements in real life are just shaped like cylinders. So a resistor a lot of times will look like this. It might have a raised end. A resistor usually has some stripes on it. The stripes are actually a color code for how strong the resistor is. But most people don't read the color codes anymore. So even if this stripe pattern could tell you that this is like a 1200 ohm resistor, realistically, maybe what you would look at is say this is a red, orange, black resistor based on the colors of these stripes. So maybe this is like a red, an orange, and then I guess these are already black. A black and a black. Something like that. At this point, we more or less use the color code as a identifying tag versus having a specific meaning. The meaning's still there. We just don't really pay attention to it. So then I want to see about how a resistor is made and what physical properties of a resistor contribute to its resistance. I'm going to ask you to pretend for a moment that you enjoy milkshakes. If you do enjoy them, then you don't have to pretend. If I gave you a milkshake and I gave you two different straws to drink it out of, to choose from, one that looks like this and one that looks like this. They're the same length as each other, but they have different areas. Area 1, Area 2, I know I'm just kind of showing the diameter, but think about the area like the cross-sectional area, right? If I gave you these two straws, straw 1 and straw 2, and said which one are you going to use to drink your milkshake, everyone's going to choose straw 2, assuming you like milkshakes. And that's because the area of the straw determines how easy or difficult it is to get that milkshake. In this case, the bigger area makes it easier to get milkshake, which means this has a lower resistance. This one has a higher resistance. So I'm going to say that resistance is proportional to area. I know I wrote that with some weird spacing, but there's a reason. Now if I gave you two straws, one that looked like this, and one that had the same area, but looked like this. So same area, but this one's got a length of L, and this one's got a length of more than L. Length is more than L. I don't know. If I asked you which one you would use to drink a milkshake, you would say this one on the left. The one on the right might be more fun, and if you were having a very easy to drink, that's probably the one you'd go with. But for something that's going to take some effort, you're going to use the straight, like the shorter straw. So this one has a lower resistance. This one has a higher resistance, meaning resistance is directly proportional to length. Directly proportional to length, inversely proportional to area. And then we're going to have some kind of a coefficient. This thing is called the resistivity, because we didn't have enough words that sounded like resistance. This thing is called the resistivity, and it is a property of the material. If I have two identically shaped pieces that I wanted to use for a resistor, and one of them is made of steel and one of them is made of rubber, then you know the one with the rubber is going to have a higher resistance. So this is resistance by definition. Back here we talked about what a resistor does. And then the one other piece that we would like for resistors right now is what mathematically does a resistor do in a circuit. So I'm just going to draw a very simple circuit. Something like this. If this is a 12-volt battery and this is a 2-ohm resistor, 20-ohm resistor, this battery is going to try to put some current through here. That current's going to pass through my resistor and come out the other side the same. There is a relation between how much voltage drops across that resistor and the current, and it looks like this. We call this Ohm's law, and it says that the potential difference across a circuit element, across a resistor, specifically a resistor, is equal to the current running through it times the resistance. We are going to soon take these circuits and take circuits with many resistors and break them down to be one equivalent resistor. But when we are down to a battery and a resistor, we can say our current is equal to the voltage of the battery divided by the resistance. So in this case, 12 volts over 20 ohms equals 0.6 amps. That's it for resistors for right now.